Good afternoon to everybody who's joined this BCSA webinar. My name is David Moore. I'm the Deputy CEO here at BCSA, and it's my sort of pleasure this afternoon to actually give you a webinar on what I call stealing fire. So if you bear with me for a couple of seconds while I share the screen. Hopefully you can all actually see the first slide, which is titled Stealing Fire. I put this presentation together because I've noticed that there's been a lot of interest over the past few years on how buildings perform in fire. And I've actually got a lot of questions from BCSA members and the wider industry on, well, what regulations should we follow? What's the fire resistance period? How is it calculated? What's an approved document B? So I felt I'd put a presentation together to look at some of those issues going forward and to address a number of things. So we're going to actually look at, in this presentation, the building regulations. And the building regulations is a devolved activity, so it's actually different from each country in the actual UK. We'll look at that. We'll look at how you comply with building regulations. What does the law say? What do you have to comply with? And we'll look at actually the guidance actually given by each of the countries in the United Kingdom as to what they're saying about buildings and the fire resistance period for each building. We'll then look at how we go about demonstrating that products, be they steel, concrete, timber, actually comply with actually the fire resistance period using things called the standard fire tests. And we'll look at the failure criteria. What is considered failure when you're actually doing a fire test? We'll also look at the properties of steel at elevated temperatures and effects of load and gradient, temperature gradient, and your fire Eurocodes themselves as well for actually looking at the design of the elements in fire. We'll talk about the standard fire test in a bit more detail, but we'll look at the actual limitations, because there are limitations. It doesn't actually compare with a real fire, and we'll actually show you a graph showing the comparisons between the standard fire test and real fires. And then I'll spend perhaps the bulk of the presentation looking at full-scale fire tests, looking at all the work we've done over the past probably 30 years, looking at the forms of steel frame buildings, not just elements in fire. And I'll make use of the work I did at Cardington, and we'll show you a few slides and videos of real fires and real buildings and how steel really performs in fire. And then lastly, I put together at the last minute a few slides on open-sided car parks, following the actual Luton car park fire. I've had a number of questions on that. So just some ideas and some thoughts basically I'm sharing on performance of open-sided car parks. So let's start. So as I said, the actual building regulations is a devolved activity, and we have a different set of regulations in England, Wales, Scotland, and Northern Ireland. And I'm just showing on the screen the actual first page for each of the actual regulations. So this is the law, this is what the law says on performance of actual buildings under different conditions. In terms of the regulations, they're what we call sort of performance-based. It tells you how the actual building, how the actual structure should perform. It doesn't tell you how to actually achieve that performance. So it doesn't actually give you prescriptive terms. It doesn't tell you what standards to use. It doesn't tell you what fire resistance period to actually adopt. It just gives you a statement saying on how the building should perform. An example of that is given on the next slide. This is the actual regulation taken from the building regulations in England, and this is actually referred to as clause B3.1. And I'll just read it out to you. So this is the law. It's what the law says about the performance of buildings in fire. So the building shall be designed and constructed so that in the event of a fire, its stability will be maintained for a reasonable period. So it's a performance-based legislation. It tells you that the building must remain stable for a period of fire resistance, but it doesn't tell you what the reasonable period is. It leaves that up to you as the engineer to actually sort of decide that and to actually demonstrate to the authorities that your design will actually meet like their view on what is a reasonable period of stability for the building in the event of a fire. We have the same or a similar clause given in the building regulations in Scotland, and this is clause 2.3. Similar, but perhaps gives you more information on what it means by reasonable. So again, I'll read it out to you. Every building must be designed and constructed in such a way that in the event of an outbreak of fire within the building, the load bearing capacity of the building will continue to function until all occupants have escaped or been assisted to escape from the building and any fire containment measures have been initiated. So there's more information in this particular piece of legislation on what constitutes reasonable. So clearly, the load bearing function of the actual building must be maintained. And people must be allowed to escape either by themselves or with some kind of assistance. But over and above that as well, the fire brigade must actually have time to get in there to actually contain the fire in some way or to start the containment measures of the fire. So there's a bit more information given in the Scottish regulations as to what needs to be achieved. But again, like the English regulations, it doesn't say how to achieve it. It doesn't give reference to standards, either the Eurocodes or British standards. It leaves it to the engineer to decide how it's achieved. Having said all of that, each country does actually publish some guidance documents giving you more information on what reasonable means in terms of fire performance. And in each of the actual countries in the UK, we have a different set of guidance documents. We have on the actual left there is approved document B, fire safety. This is volume 2. There is a volume 1 for dwellings. This is volume 2 for buildings other than dwelling houses. And that's the English one. We have next to that a similar one for Wales. And then we have the one in the middle is the one, it's a technical handbook for non-domestic buildings, Scotland. And then at the end there, we have Northern Ireland. So we have a set of guidance documents. This guidance is not legislation, which tell you how to actually comply with the legislation given in the building regulations. Effectively, the guidance given in these documents is taken as deemed to satisfy. If you actually follow the guidance of the document, you're deemed to comply with the actual legislation given in the building regulations. If you do something different, then you'll have to actually demonstrate to authorities that what you're doing does actually comply with the actual legislation. Just to give you some idea what's included in approved document B, this is the one for England. This is a picture I've taken from table B4, which gives the minimum period of fire resistance for different types of building. And on the actual vertical axis, you have the actual building itself, whether it's a block of flats, whether it's an office, whether it's a shop or commercial or industrial. And then further on, you have the fire resistance periods, depending on the height of the actual building. So effectively, the fire resistance period for the building is dependent upon occupancy, type of building it is, and on the height. So we're looking at basically fire safety for people actually escaping their building. Obviously, the higher the building, the longer it's going to take. Buildings actually with people who actually have difficulty getting out, again, like hospitals, the longer the fire resistance period. And I've identified sort of two with the red clouds. You've got the first one coming down the right-hand side is for offices, and you've got two types, one without sprinklers and one with sprinklers. And you can see that if you've got an office which is more than 30 metres tall, you cannot have one without sprinklers. It's not permitted. With a sprinkler system, it has to have a fire resistance period of 120 minutes. Coming further down, we've got an assembly or recreation, and again, there's two types there, one without sprinkler systems, one with. This is for a building which is up to 30 metres high, and without sprinklers, you're allowed 90 minutes. And if it's sprinkled, you get a lower fire resistance period, which is 60. So the information on the fire resistance periods for different types of buildings is given in the approved documents. Similar information is given in the approved documents in Scotland, Wales, Northern Ireland. On the next slide, we talked about sort of open-sided car parks. We've seen the performance of the Luton car park fire and other open-sided car parks. I just thought I'd take the time to actually sort of show you the regulations or the guidance given in approved document B for England. This is for an open-sided car park. The red cloud shows you that for an open-sided car park up to 80 metres high, fire resistance period is 15 minutes. And there's a link, a reference to note 7 and note 8 in the table. Open-sided car parks are given a particular definition in terms of the actual sort of size of the openings actually in the actual car park itself. And then item 8 below gives you some idea of the type of beams and freestanding columns and bracing that can actually be used without fire resistance protection. I'd also point out that it might seem very strange, but approved document B in England actually doesn't make any reference to, any direct reference anyway, to the Eurocodes or to actually British standards for fire. The only reference I can find to actually the Eurocodes is the one given at the bottom of the table here, where it says guidance is available in BSEN 1993-12, which is the Eurocode for actually the fire performance of steel in fire. All other references to Eurocodes, so the general reference to Eurocodes and British standards was taken out a few years ago. Not quite sure why, but there's no direct reference to British standards for fire design or the Eurocodes themselves. So we've looked at the building regulations, looked at the performance criteria it gives, we've looked at the approved documents and the information it gives on fire resistance periods. How do we actually sort of demonstrate to the authorities that the structures we're building, be they beams, columns, floors, etc., actually meet the fire resistance period actually given in the approved documents? Well, the most common approach, most common route is to actually do that through a fire test. And we have a series of regulated requirements for actually different, what we call standard fire tests under standard fire conditions. And we carry out tests on structures such as beams and columns and walls and floors. We expose them to what we call the standard fire exposure and the actual conditions under which we actually erect or we actually build the beam, the column, must represent the conditions they'll see in the actual structure in terms of the fire exposure, the loading, the support conditions. All this information is set out either in the national standards or in the European standards for fire testing different products. So when it comes to actually looking at a fire test, what is the actual time temperature curve that we actually use? And this particular slide gives you the temperature on the vertical axis and the time on the horizontal axis. And you can see the yellow line on the actual graph is the actual time temperature curve. It's called the actual standard fire. And it's given in various documents, be it BS 476 or the European standard for load-bearing elements. And this is the actual sort of fire curve we actually expose the different elements to actually determine their performance. So it's looking at actually how you determine the fire resistance period for a particular type of element. When we carry out a fire test on a beam or a column or a floor, we have to think about the actual the mode of failure. And there are three different ways of actually classifying failure of a structure or an element. And these are listed on the actual slide here. The first one's probably the easiest one to get your head around, and that's the load bearing capacity, the resistance to collapse. We might have a column in a furnace, it's got a load applied to the actual ends. We actually subject to the column to the standard time temperature curve, and when it starts to collapse, that would actually be the temperature at which the column fails. But there are other failure criteria. And the second one here is the resistance to fire penetration. And it's called the integrity of the actual element. And this might apply to a floor where you've actually got the fire underneath and you're looking at the actual penetration of the fire through the floor to the unexposed side of the actual flooring system. And that could be where you see flames coming through, but it can also be done where you actually put a cotton swab on the top of the actual floor, and that might catch fire just through the actual sort of the temperature of the floor itself. Insulation is another one where you might get excessive heat on the compartment below a floor, and you're getting effectively the temperatures transferred through the floor such that the unexposed floor is getting hot. And there's actually some criteria for that. So the unexposed face shouldn't have an average temperature more than 140 degrees centigrade, and there shouldn't be a maximum temperature above 180 degrees, and that's considered the insulation failure. So there are three different sort of types of failure that we actually look at when we're doing sort of fire tests, and they apply to actually different types of elements. So for instance, a column, the only failure criteria for the column would actually be its load-bearing capacity. But if you're looking at a floor, which forms part of a fire compartment, you'd be looking at all three. We're looking at its load bearing capacity, it shouldn't fail. You were looking at its integrity, the resistance to fire penetration, and you were looking at the insulation, so the actual unexposed side of the actual floor doesn't actually get sort of too hot. So those are the actual three criteria we're actually looking for when we're actually doing a fire test. I've just put a couple of slides together so you can get a picture of the standard sort of fire test we carry out. This is a standard column fire test. There's a furnace where you put gas in the furnace. We follow the actual standard time temperature curve. The column itself might be loaded, and it's the temperature at which we get failure that gives us the actual fire resistance period. The second one here is a beam fire test. You can't quite see the beam, which is actually under the furnace. You can see the cartilage or the actual loading applied to the actual the beam or the floor. And again, in this one, we actually subject it to the standard time temperature curve. And we have the sort of three different modes of failure we will be looking at to actually determine the actual fire resistance period for this particular element. So we've had a quick look through at the building regulations. We've had a quick look through at the approved document and the fire resistance periods. And we've had a look at the way we actually determine the fire resistance period using furnace tests and using the actual standard time temperature curve and using the different sort of failure criteria. But there's also lots of work been done over the past, probably 30, 40 years on the performance of materials at different temperatures. And we know a lot about the way steel behaves. And this particular graph on the screen shows you the strength factor on the vertical axis against temperature on the horizontal axis of a typical grade of steel. As it gets hotter, it clearly actually gets softer and the strength factor reduces down. Back in the early days, when we actually used to do permissible stress design using things like 449 and the other versions of BS 5950, we used to actually do permissible stress design where a member was allowed to actually take 6% of its room temperature strength. And from that, from this graph, you can see that based upon 60%, the actual steel section that's actually subject to a uniform temperature will actually last 550. And for a long, long time, that was actually seen as the limiting temperature for actually any steel beam, any steel column, etc. But that's not the case. A lot of research has been done to show that you can actually get higher failure temperatures depending upon the temperature profile in the actual steel section and depending on the load applied. I just want to sort of give you an illustration of that in the next slide. So here we have a couple of eye sections, and the one on the actual left is an eye section which is subject to fire on all sides. And you can see that that's actually got a uniform temperature from the top flange to the web to the bottom flange. And we've actually put on that a load ratio of 0.6. And in that case, the failure temperature will be 550. But then we actually look at a more realistic structure. If we look at the actual one on the right, we've actually got a structure which has got a concrete topping on the top flange. It's subject to a fire from actually the bottom flange. And you can see because you've got a heat sink of the concrete on the top flange, which is protecting the actual top flange as well, you get actually a distribution of temperature where you get the bottom flange is hot, the top flange is a bit cooler. And as the bottom flange gets hotter, the actual load is transferred to the actual cooler parts until you actually get sort of failure. And in that case, the maximum temperature that that particular configuration will actually see is 620 degrees centigrade. So it's actually quite different from the actual approaches we had in permissible stress design that we now have in the ultimate stress approach. We can go further than that. We can actually look at another section on the actual right-hand side. It's the same as one in the middle. We've actually got an eye section supporting a concrete slab. But on this case, we've actually got a lower load ratio. So here the load's lower at 0.25. And in this case, because we've got a lower load ratio, we've got an asymmetrical distribution of temperature within the actual section because of the protection from the concrete on top, we can actually get a temperature of 750 degrees centigrade. So it's not sort of fair to say that the maximum temperature that a steel beam can reach is 550. It does depend upon the actual construction. It does depend upon the actual heat sinks that are available. and the actual load that's actually applied to the actual beam itself. So we can actually get significantly larger temperatures in the actual beams depending on the form of construction. A lot of this information was actually first included in the world's first design code, as it says there, for fire, which was BS 5950 Part 8, published in 1990 and redrafted again in 2003, based upon fire tests that Tata Steel carried out, now called British Steel, of course, and tests carried out at the Building Research Establishment. And this brought all the actual methods together for achieving fire resistance of steel beams and columns. So it's based on the standard fire test, and if you want to look at the background, SCI has a publication which is P80, giving the background to this particular standard. It's based upon all the information I've shown you before. Of course, now things like 5950 Part 8 are being withdrawn by BSI, and we now have a new series of standards in place. We have the Eurocodes, and there's a whole suite of actually Eurocode standards. We're actually looking at the performance of different materials in fire. So I've just given you three on the screen here. You've got Eurocode 11.2 is the actions or loading. So that's you're able to actually work out the actual time temperature in the actual compartment using that document. And then Eurocode 3, design of steel structures part 1.2, is clearly for steel, looking at the forms of steel elements actually in a building. And then the final one on the right there is composite, looking at the performance of steel and concrete structures in fire. But there are other ones for those interested in aluminium or interested in timber or masonry. There are actually Eurocode fire standards for them. And they're being updated as I speak. So in about a few years' time, I think it's March 2028, we'll actually see new versions of each of these Eurocodes coming out. So look forward to that. We've talked about the standard fire test. We talked about the standard fire test being used to actually predict the fire resistance period for different elements, but it does have limitations. And I want to just point out a certain number of limitations with this graph here. So again, it shows temperature on the vertical axis and time on the horizontal axis. And there are two graphs shown on that. There's the blue line, which is the standard fire, the standard time temperature curve we use in our furnace tests. And the actual green line is a real fire. I think just by looking at it, you can actually see significant differences between the two. The blue line, the standard fire, increases rapidly at the start and then begins to tail off. And then the actual temperature increases ad infinitum. This particular standard fire does not go out. It keeps going on. If you look at a real fire, the actual green line, you can see that we have a growth phase at the start, where we have the material in the compartments beginning to actually catch fire, beginning to develop temperatures. And then we get to a stage where all the material in the actual compartment is on fire and we get flashover, where we get rapid developing temperature, etc. And then eventually it levels off as material is being consumed. And then we get the decay phase, where the material is being consumed, it's being burnt, etc. And we get a reduction in temperature. So you can see what I'm pointing out here is that the performance of an element, a member in a furnace subject to the standard time temperature curve bears no resemblance to actually how an element might perform in a real fire. The standard time temperature curve is used really to actually look at the performance of different elements. But as I said, it bears no resemblance to actually how an element might perform in a real fire. So 60 minutes fire resistance is 60 minutes fire resistance in the actual the standard time temperature curve, not necessarily 60 minutes in a real fire. It could last considerably longer. So I looked at the building regulations, we looked at the approved documents, we looked at standard fire tests and how we can actually work out the fire resistance of different elements and the failure criteria. I looked briefly at the performance of steel in a real building where a composite beam might perform somewhat differently to a bare steel beam. And I want to look at how real buildings perform. And I start with actually a building which is called Broadgate Phase 8. And that was under construction in the 1990s. And on the 23rd of June, 1990, the building was partly complete. It's a steel frame with a composite floor. There's no fire protection on the actual columns, no fire protection on the actual beams at the time of the fire. So the fire was actually engulfing the building, if you like, at the construction stage. It started in a contractor's hut on the actual first floor of the actual building. And the fire lasted for about 4.5 hours. And temperatures actually in the building were thought to exceed about 1,000 degrees centigrade. So this is a building traditionally built in the 1990s to the actual standards at the time. Steel frame building with a composite floor with no fire protection on the elements, beams or columns. So how did it perform? So this is a picture from inside the building after the fire. And you can clearly see there's no fire protection on the columns, there's no fire protection on the actual beams, etc. But there's no collapse. The flooring system hasn't collapsed, the columns are bent and distorted, the beams are bent and distorted, but there's no collapse of the actual floor. And yet, at the time, if we'd have actually been predicting how this building performed at the time, we would have said it would have actually failed. So back in the 1990s and the 2000s, we were left with a conundrum, which is, how did this building survive? And at the time, I was working for an organisation called the Building Research Establishment up at Watford, and they had a series of hangars which they used, and this is a hangar just south of Bedford, and it was used for actually conducting fire tests. So I made a case to Treasury that I'd like to actually build real buildings inside the hangar and set fire to them. So that went down well. And in this little video I'm showing you, you can see sort of 3 types of building. You can see this is a concrete building. This is a reinforced concrete building, full size, 7 stories high. The one actually furthest away from you is a 6-story timber frame building. And the one coming into view is the one I want to talk about a bit more. The first building to be built at Cardington is an 8-story steel frame building built to the actual current design standards at the time and fabricated to the current design standards as well. So let's talk a bit more about it. So this is the actual building you can see here. It's 8 stories, steel frame. It has an area of 21 meters by 45 meters long, 33 meters high. Consists of 5 9-meter bays along the long side and bays of 6, 9, and 6 centers throughout its width. It has 3 lift shafts, one at either end and one in the center, giving you the stability to the structure. It's designed as a traditional braced frame. The beams are designed as timber supported. They act compositely with the actual composite floor, and the floor is a 130mm slab with steel trapezoidal profile metal decking and lightweight concrete and an A142 anti-crack mesh. So a traditional form of construction designed by my friends at Peterborough and fabricated and erected by Corntons, who are still around doing great structures. And we conducted all sorts of tests on that building, but perhaps what it's best known for is the series of fire tests we conducted. And this particular plan shows you the 7 different fire tests performed in different parts of the building, ranging from fire tests on simple beams to fire tests on almost half of a complete floor. So you can probably see the green sort of dotted lines on the left-hand side, which is actually the 5th fire test. It was the largest, and that has a floor area of 324 square meters. The one I want to focus on is the fire test number 7, which is the red at almost the right-hand side of the screen. And that's a compartment which is 9 meters long by 6 meters wide with a central beam and obviously 4 columns at the corners. That's 77 square meters, and it was done in conjunction with the University of the Czech Republic and with the Portuguese University at Coimbra University in Portugal. And I just want to go through and look at the performance of that. So this is the compartments that are being constructed, where we've got plasterboard walls going around the actual sort of internal walls. And you can see basically the plasterboard wall there. And you can see on top of that, you've got rock wool, which acts as a wall, but actually a flexible wall. So it's allowing the actual steel sections to come down as they deform under the actual heat of the fire. And you can see the front of the actual compartment on the right-hand side at the top there, and then some idea of the internal compartment inside at the bottom. Then moving on, in terms of actually loading, the loading is actually done by dead weight. So we have sandbags which sit on the top of the floor. We debated long and hard whether to use sandbags or water, and we decided that sandbags were actually more convenient, easier to move around. And the sandbags on the actual floor represent the 100% of the permanent dead load, and 100% of the variable permanent dead load, and about 56% of the actual live load. As I said, it's with sandbags. I think they're, if I remember correctly, 10 kilonewtons per square, 10 kilonewtons over 1 meter square base at 1 meter centers. So, and that actually remains on the actual floor throughout the entire fire. It's not removed, so the deformations you see are real, and the performance of the structure, again, is real in the fire. It's supporting the load still in the fire. We then look at the actual fire load itself, and we have a way of sort of doing that using what we call timber cribs. And you can see the timber cribs being put together. These are bits of timber which are 50 millimeters square and the space 50 millimeters apart. And we stack them so that we have a fire load of about 40 kilograms per square meter, which is about equivalent to a reasonable office fire load. At the time, I was a messy researcher at BRE, and I weighed my own office, and because I had paper everywhere, my office weighed just under 50 kilograms per square meter, so very untidy researcher at BRE. I want to just show you the actual fire test. So this is a little video. You can see the actual fire brigade on the actual right-hand side. It's the Bedfordshire Fire Brigade who came along just in case anything went wrong. I've got a little graph at the actual bottom left-hand corner, which is showing you the actual time temperature in the compartment of the fire itself. So we lit the fire, lit the timber cribs, and closed the actual door on it, and just stood back, monitored the actual temperature in the actual compartment, monitored the temperature of the actual steel beams and the flooring system. Clearly took lots of videos as well. There's also a heat-seeking camera that actually measures the actual temperature profile in the actual connections inside the actual compartment. Unfortunately, I don't have a video of that just yet. But you can see the actual fire developing. You can see the timber cribs are beginning to actually be consumed. This is about sort of 25 minutes after the start of the fire. The temperature is approaching about 800 degrees centigrade. Bearing in mind that this compartment has no fire protection on the actual main beams in the actual compartment. The columns are protected, by the way, but not the actual beams. So we're trying to simulate in some way the actual the fire we actually saw at Brogate, and to try and establish, just what happened in terms of structural behaviour, but it actually stood up. So we're approaching just over 30 minutes. The temperature is beginning to level off a bit. You can probably just see from that video shot, the actual main steel section is beginning to actually deform. Little columns you see hanging down, what we call indicatives, they're just there with different types of incandescent paint on, so you can see how they perform in a real fire. We can go to sort of 40 minutes, the temperatures begin to rise even more. We've probably got about 850, 90 degrees centigrade in the actual compartment at the moment. We're getting towards flashover where everything's actually involved, all the actual timber cribs are involved in the fire. And you can see the temperature again beginning to actually go up even rapidly now. So we're approaching 1,000 degrees centigrade, and we're going to go up to about 1,100 degrees centigrade in this fire compartment. I mean, bearing in mind all the information we had prior to these tests on the performance of elements, we would suggest that this structure should have failed well before now. We're getting up for about 50 minutes, got about 1,100 degrees centigrade in the actual compartment. The timber cribs are being consumed. We're now going to the decay phase and things are cooling. Again, you can get some idea from the video, the deformations you're actually seeing on the actual main steel beam in the fire compartment. And comparing those with the actual fire we saw at Brogate, it's a similar type of performance, it's a similar type of deformation. So we're coming to the end of the fire, it's over 2 hours, 2.5 hours from the start of the fire, and we get our first shots now that the compartment has actually survived complete burnout. Almost 3 hours, so 2.5 hours into the actual fire test, we've got large deformations that we saw basically at Brogate, but it's standing up. And the question is how? I put together a little slide here which shows you some information from the actual fire test itself. We've got the time on the horizontal axis and the temperature on the vertical axis, and I plotted a number of temperatures from thermocouples in the compartment and compared those against some of the actual code predictions. So let's just look at the actual sort of temperatures of the compartment. So firstly, we've got a blue line, which is the actual temperature at the front of the compartment. And secondly, we've got a red line, which is the temperature at the back of the compartment. You can see at the back of the compartment, the temperature is considerably higher than at the front. Here we've probably got heat being reflected from the actual back of the compartment into the compartment itself, giving rise to actually a high temperature. But where you've got ventilation, where you've got the possibility of the actual heat being vented from the compartment at the front, you have a much lower temperature. So the difference between the two is just over 200 degrees centigrade. The other two graphs are actually worth pointing out as well. So the first one at the top there, the mauve one, which is from Eurocode 1.2, predicting the actual time temperature curve from the material in the compartment. You can see that whereas it doesn't exactly follow the actual temperature profile in the compartment, it is actually a good predictor of the maximum temperature. The other line is the standard fire curve, the green line, and you can see that that bears no resemblance to the actual performance of a real fire in a real building. It goes up rapidly at the start, tails off a bit, and continues to actually increase ad infinitum. So it's, you know, has its limitations, does the actual standard fire curve. Going on to actually look at some of the performance in the actual compartment itself, I've got a number of pictures here taken inside. This is the actual secondary beam supported on the primary beam with a simple fin plate. And we can see we have buckling of the actual sort of bottom flange there of the actual secondary beam. And the question is, you know, how is that occurring? And our suggestion is that as the temperature is increasing, the actual beam sort of getting longer, eventually it butts up against the actual, either the beam or the actual column, and you get a combination of restrained tensile forces, so compression forces in the actual bottom flange, together with the actual temperature reduction, temperature increase and reduction in strength gives you a buckling behavior on the actual bottom flange. So this is giving us an insight into not just how the building behaves under the fire load, but how the building behaves under the cooling program as well. So here's another connection. We're looking at an end plate, a flush end plate connection. This is the main beam going into the actual column. You can see you've got buckling of the actual column, you've got buckling of the actual sort of beam, which is coming from what I explained before. But you've also got fracture of the weld at one side where you've got the end plate. The other side is still intact, by the way, and still supporting the actual floor. But again, we asked the question, how you've got fracture there? And we think that's due to the actual cooling phase, where you've got the beam is now a little bit shorter because it's buckled. It's cooling down and contracting, and that contraction is putting actually lots of tension into the end plate connection and causing fracture of the end plate there. Interesting, the actual bolts are not protected, and the bolts are actually still intact. Sorry, you can probably hear a fire alarm here in the office. That's just gone off, so it's just a trial, I think. Moving on, we have some more pictures showing local buckling of the actual bottom flange of the beam in more detail there. And then going on to the next slide, we have a picture of the actual top of the floor itself, and you can see you've actually got sort of cracks in place, etc. So maybe the insulation failure would actually apply here. But you can also see the reinforcing bar there as well. And this is actually a picture of the inside of the compartment after the actual fire, and then we took a whole host of actual measurements on the actual top of the floor, looking at the actual deformations in the actual floor itself. And I think in all these tests, we were aghast at the sort of deformation that you get in this flooring system. I mean, I know we talk about sort of a few millimeters for serviceability movements, but here we've got a deflection in the center of the actual floor of 925 millimeters. On a base size which is sort of 9 meters by 6 meters. And this led us to the conclusion, after sort of lots of sort of research and theoretical work, But what we've got happening here is what we call tensile membrane action. Effectively, it's the actual reinforcement in the actual concrete floor, the composite floor, that's acting as a tension membrane, which is basically spanning from actually one side of the compartment to the other, and is actually supporting the floor itself. And this is a mechanism that we think actually happened at Broadgate to actually give you the performance of the actual flooring system you saw there. So we have, if you like, identified with these full-scale fire tests different modes of behaviour, which can actually be used to look at enhancing the fire performance of actually steel frame buildings with limited, or in some cases, no fire protection on the actual main supporting beams and columns. So I've been through the regulations, been through the approved documents. I've shown you actually some of the fire tests we're doing, standard fire tests, showing some of the limitations of those, and then looked at the performance of real buildings in real fires and showed you how we actually get other, at the time, unusual modes of behaviour, which actually give rise to a better performance in a real building than you can get by predicting from isolated members. And it's these real performances that I think we actually need to use to enhance the performance of real buildings going forward. As I said at the start, I've had lots of questions on car parks and oversized car parks in fire. And I thought I've literally just put a few slides together to actually put my thoughts together in no sort of logical order, really. And I start by looking at the Luton car park fire. And I think we all saw, perhaps on the TV, the actual fire in that car park. Started at about 9:15 on the 10th of October. It was in Terminal Car Park 2 at Luton Airport. There's various reports coming out which suggest that the damaged vehicles were 1,300, 1,400 vehicles damaged or destroyed in the fire. And the Bedfordshire Fire and Rescue Service carried out a report. Initially, it thought the fire might not be accidental, but actually after further investigation, it was found that it was accidental. There was some discussion about the fire being an electrical vehicle or a hybrid vehicle, and that's not the case. The most probable cause, according to the Bedfordshire Fire and Rescue Service, was an electrical fault in the engine bay of a diesel-powered vehicle. It was not a hybrid or plug-in hybrid or electrical vehicle that actually started the fire. The actual collapse, I think, was significant, and I'll show some pictures that I've pinched. So this is coming from the sort of BBC's website, and you can see the type of failure you've actually got in the car park. I should say at this stage that in terms of actually complying with the legislation, the car park met the legislation at the time. So oversized car park legislation is 15 minutes fire resistance period. And in terms of life safety, no one was actually sort of killed. There's no fatalities in the actual fire. So it performed as it should have done under actually the legislation or the building regulations. Having said that, I look at the damage and I think that we've got here a single spanning sort of composite slab, and we've got some kind of fracture of the actual composite slab over the actual sort of central supporting beams, and this is leading to the actual sort of failure of the floor and the collapse of the floor in various places. And here you can actually see it again, that the floor's collapsed and some of the cars have actually dropped on the floor below. And then on the next slide, I've got again the collapsed material. And the reason I'm showing that is that you get more of a feel for the type of construction. You can see on one of the beams the shear studs, you can see the actual sort of decking, and you can see the actual composite slab with the reinforcement in. So I think structural behaviour is an issue, and in looking at the actual Luton car park and other car parks, I put some thoughts together and thinking, well, let's look at the fire tests on which the regulation was developed. Let's look at the structural behaviour, because in comparison to Cardington, in comparison to Broadgate, the structural behaviour wasn't as those behaved. And perhaps the definition of oversized car parks might need changing in terms of actually location to other buildings. If it's close to another building, then the ventilation from the heat from the actual sort of car park might not be as we actually want it to be. And the size of the openings, are they again large enough? Should they be larger? And then we have people asking questions about heat release from modern vehicles. You know, do modern vehicles actually give out more heat electrical vehicles and hybrid vehicles using large batteries, is the heat different to actually a petrol or diesel vehicle? And the number of cars involved in fires, it's difficult to predict, and I'll show you some examples of the number of cars involved. And then suppression systems. In building regulations, we think about life safety, but clearly in some of the car park fires, we've seen damage to actually large numbers of property in terms of vehicles. This is at the moment not controlled by building regulations, but if it was to be, or a client wanted to be, I think a suppression system might actually be the best approach rather than thinking of actually increasing fire resistance periods. I put on the slide a couple of slides showing open-sided car park fire tests that were carried out back in the 1990s and early 2000s. This is an open-sided car park carried out by a combination of CTICM in France and Arbed in Luxembourg and TNO in the Netherlands. It's an open-sided car park, as you can see, which has a floor area of 480 square meters. The beams and columns in this case are actually European section sizes, so HEA 180s for the columns and IPE 500s for the actual beams, with a composite slab of 120 millimeters thickness. And there were sort of 2 fire tests carried out on this with different types of car. I think you'll all start to laugh when I say at the time these were modern vehicles. They were obviously modern at the time, back in the early 2000s. I think on the next slide you can get an idea of the type of cars we're talking about, which looks sort of quite old-fashioned today. But at the time, it was felt they were modern, and it was felt the actual amount of combustible material used in these vehicles was different to the actual earlier models, and this might lead to actually a different type of fire. So fire tests were carried out, and here's a rather poor sort of video, a poor sort of picture of the actual fire tests in the actual fire compartment. And they concluded from the fire tests that the new generation of cars were more severe in terms of heat release from those that actually being used in the 1970s and 1980s. But the actual fire test shows that actually with the fire test they undertook, an unprotected steel frame car park with a composite floor could actually survive full burnout of these cars without the risk of the actual floor collapsing. So I go back and look at the structural behaviour and think, well, we can still base the structural behaviour on the actual fire resistance periods given at ADA. And if we actually used a composite flooring system and we have continuity of reinforcement and continuity of the actual decking above the actual sort of beams, as shown in Cardington on the right rather than on the left, then we should be able to actually develop and design a flooring system that's able to survive full burnout without the risk of the actual floor collapsing. If we get the sort of behaviour we've actually seen at Cardington and we see it at Broadgate. Other thoughts is that open-sided car parks do rely on ventilation, and they get ventilation from clearly the actual the height and width of the actual sides of the actual building which are open. And I think perhaps that might be need looking at in terms of, is the actual ventilation area sufficient? There are sort of definitions of that given in the approved document B in England, it's given on the screen here. And then the location of the building. Clearly having an open-sided car park next to actually another building is probably not the right approach, and there should be perhaps some distance that should be built away so you can actually get the ventilated heat from the actual car park. That's something perhaps to think about. Other things to think about, people keep talking about heat release rates for modern vehicles, saying the electrical and hybrid are different, and that you might get hotter faster than actually traditional sort of petrol and diesel, and how many cars should you actually be designing for in a car park fire. I've just got a couple of slides on that. So this is one slide that was actually in an article in BCSA's New Steel Construction magazine. This shows heat release rate on the vertical axis and time on the horizontal. The red one is actually a van, so that's quite different from actually a car. And the other 3 graphs are actually for cars. So the black line or the grey line is for the older sort of diesel petrol type vehicles, giving the heat release rate over time. And then the next 2 are a modern vehicle, that's the orange one, and then the electrical vehicle, which is the actual blue one. And I think the main thing to take away from this graph is that the heat release rate of modern vehicles, be they electrical or hybrid, it's very, very similar to actually the older type of sort of petrol and diesel. So there's no really change in the actual the fire that you actually might get in an open-sided car park from modern vehicles. The other thing I've been asked about is, well, how many cars should you design for? And that's quite difficult. I put on the actual screen here a number of car park fires ranging from the Stansted one in 2010, the one in Germany in 2014. So Stansted's got 24, Germany's 73, and the Echo Arena in Liverpool car park fire was 1,400, and the one in 2019 in Cork in Ireland was 60. Balloon car park fire, 1,300. So it's very difficult, I think, to actually sort of do a design to estimate the number of cars that might be on fire. And it might be that the standard time temperature curve here is actually a better, perhaps more conservative approach to adopt. So we'd still be adopting, if you like, the standard time temperature curve. But as I said, with the sort of restrictions and limitations in the past, it doesn't actually bear any resemblance to actually a real fire, and might be in many cases more onerous. So 15 minutes in a standard time temperature curve might actually be significant in a real fire. So these are my thoughts for open-sided car parks. Perhaps we should look at the definition of an open-sided car park, look at the location, the size of the opening, structural behaviour. We should think about perhaps having a composite floor using continuity of the reinforcement and the actual decking to get tensile membrane action to improve performance. If we're looking at sort of fire resistance from a life safety perspective, then the heat release rate for modern vehicles is very similar to older vehicles, and therefore there's no case for actually a change the fire resistance period in approved document B, and we can base it on the standard fire. But if we are looking at property protection, increasing the fire resistance period for the actual building won't protect your property, but actually considering the use of a suppression system might. So it's some thoughts, if you like, going forward for open-sided car park. This is my last slide. So it's been a sort of a long presentation. We've looked at lots of things going forward. We've looked at the building regulations, how they're actually devolved, how there's slight differences between the actual law for performance of buildings in fire. We've looked at how we actually comply with that, looked at the actual fire resistance periods given approved documents, looked at complying with that with the standard fire tests and the actual failure criteria and the actual limitations of the actual standard fire test when compared to actually a real fire. And then I've spent some time looking at how steel behaves in fire, and in particular looking at real buildings subject to real fires based upon the actual Broadgate fire and based upon the actual tests that were carried out at Cardington. And then I've finished with a few slides I've thrown together looking at open-sided car parks. I hope you've sort of enjoyed the presentation. If you have any comments or questions, I believe there's a Q&A tab at the bottom of the screen. If you want to sort of put a few questions in there, I'm sure that we'll try and answer as many as we can in the next few minutes.
Thank you very much for that informative webinar, David, and for giving us an insight into your days as an arsonist engineer. We do have a few questions. So the first one, what effect does a protective paint system on the beam have in terms of its performance under fire?
Well, clearly it'll actually give you a longer period of fire resistance. You have a protected system, it actually protects the beam, be that actually incandescent paint or a spray or a board, that will clearly actually give it will keep the beam cooler and give you a longer period of fire protection.
Thank you. Sorry. What could have happened if the columns failed during the fire test of that multi-storey building? So I assume this is Cardington. Was the building designed to withstand disproportional collapse?
I think this refers to Broadgate. So Broadgate was a sort of modern building at the time. It was actually designed for disproportionate collapse. And it's strange is this. I'm actually, in my sort of younger days, actually was involved in some of the IRA explosions that happened actually in London, and got the opportunity to actually sort of go around the buildings after the actual bomb blast, where you've got significant actually damage to the actual columns. And the columns had effectively pulled down the building. So the columns were still there, but you've got tension in the columns because of the explosion. So it might have not have behaved quite as you expected to, but actually having designed the actual building for tying action, you have the opportunity to actually redistribute the loads around the actual damaged areas. And real buildings under real conditions do actually perform quite differently to actually the isolated elements we actually based our designs on. That answers the question. Next one, Zoe.
Is there any way to avoid the need for coat back of beams where you have an unprotected member connected to a protected member?
Right, that's a very interesting one, and it's one I've sort of come across a couple of times. I have, we're not giving away secrets now, I have actually sort of come across an approach whereby you can put in insulation sort of layer actually between the end plate at the end of the actual sort of beam and the actual face of the column to effectively actually reduce the temperature that's actually taken from the actual beam into the column. So if the actual the cutback at the end of the beam is actually there to actually give you insulation for the column, and actually providing some kind of insulation between the actual end plate and the column might do the same function. And I believe there's at least one, if not two companies actually looking at this.
Does the magnitude of stress under load in the steel members affect the performance of steelwork frames in a fire?
Yes, yes. I think I'd try and show that actually in one of my slides showing you the eye sections with actually different loading conditions. So clearly, if the loading condition is higher, then the actual temperature at failure will be a little bit lower.
Was the decking at Luton Car Park designed as a single span to get around through deck welded studs and avoid corrosion issues with unpainted top flanges?
Difficult to actually be precise about that because the only information I have is actually from the actual pictures, but it does look like the actual decking is single span. And yes, they're right in terms of the actual protection.
What does ADB stand for?
Approved document B, and it's fire. And there are two approved document Bs. There's actually volume 1 and volume 2. Volume 1 is actually applicable to domestic buildings, and volume 2 is applicable to buildings which are not domestic.
Right, we've got a couple more questions to go. Has the use of composite metal decking been accepted within car parks?
I think the answer is yes. I mean, from the Luton sort of car park, that was a composite deck. I just think it should have actually been continuous though with the actual beams. Sorry, is that next one?
The final question, oh, and another one's coming. What's your thoughts on external plant support steel being specified as fire protected?
That's a more difficult one to answer. Can I sort of, I'll come back to that if I may, and actually put the actual answer on the Q&As.
Okay. Will making intumescent painting mandatory avoid structural collapse?
It may not. As I said, it actually reduces the actual sort of temperature in the actual steel beam. But if the temperature gets high enough, then you actually could get collapse of the actual beam or the column. Yeah.
And sorry, somebody has just asked if you could repeat your previous answer about approved document B, ADB.
So AD stands for approved document. And there's actually a number of approved documents published by the various nations in the UK. So in England, there's approved document A, which is for the structure. Look at the performance of the structure, and in that you have things like robustness. And then approved document B is actually for fire, and there's information in that for fire resistance periods for different types of buildings. And there's a whole host of other approved documents covering different subjects. You can find them on the government website. They're free to download.
Looking at the test results, can we assume in a single-storey building with galvanised sections and sprinklers, we can achieve 1 hour fire resistance? Or in single storeys, do we need fire resistance provisions for industrial use?
It'll depend upon the actual type of construction, Zoe. So I'd like to think that we can achieve 60 minutes. It'll depend on the type of construction. It'll depend on the actual sort of ventilation conditions. Yeah, you have to take it building by building, I'm afraid.
There is one more. The emissivity values for galvanized steel reflect latest information and indicate that some additional fire protection is available compared to black steel through use of galvanizing. There's a good SCI report on this, P429.
Yeah. That sounds like a question from the Galvanisers Association. So he's right that in Eurocode 3, part 1.1, the emissivity value for galvanizing has been increased. And there is, as you say, an SCI document on this.
That's all the questions for now. So thank you very much once again. The webinar will be made available on our YouTube channel, so I shall distribute the link to it once it's been uploaded. But thank you for your time, David.
No, thank you, Zoe, and thank you for all those that attended. I hope you found it helpful.